Hello, everyone. My name is Kamiński. I work for Allegro. So Allegro is the largest Polish e-commerce company. And today I'm going to talk about asynchronous programming with coroutines and with reactive libraries. So we've had different types of reactive libraries for a couple of years now. We've been doing asynchronous programming with these libraries. And about 2 years ago, maybe almost 3, there was a new feature introduced in the Kotlin language, coroutines. Coroutines themselves are like an old thing, but coroutines in Kotlin is quite new. And first, it was introduced as an experimental feature. Now it's, since the 1.3 version, it's a stable feature, so we can safely use it. And both reactive programming and coroutines, we can use them to write asynchronous code. Now, the question is, which one should we choose? Like, should we choose one, always one, and not the other? Or are there situations where there are some trade-offs that we have to make, sorry, to choose one or the other? So we're going to learn it today. And for this presentation, I had to choose one example of reactive library, and I chose Reactor. So Reactor is like this backbone library for Spring Framework, so it's going to stay for a while. It's being constantly developed, new features are added. It's quite a modern implementation, and on the other side, it has some nice features which are not available in some other reactive libraries and these features actually are very handy. And we'll actually come to that later in this presentation. So here you can have a look at a simple code with both coroutines and reactive libraries. With coroutines, the code is quite straightforward. You just write your code as you would write synchronous code in imperative style. The only difference is this suspend keyword that you have. So suspend means that your function is an asynchronous function. It can suspend its execution at some point in time, and later on, it can resume its execution. And below, you can see the same code with Reactor, and you can immediately see the differences. Whereas with coroutines, you write code which is in imperative style. With Reactor, you have to use functional style, and you decompose your application or your code into these tiny pieces of code that are like one after the other. And the other thing is you have to use operators on your reactive types. Like here, we have a map operator or a switch if empty operator. But there is also one more difference. So with coroutines, you write your code and your code just executes, you could say, line by line. If you do the same thing with Reactor or any reactive library, this code has 2 parts. In the first part, you define a pipeline of operations, like a flow of operations. So you can see it here. And in the second part, you call subscribe, which actually executes the whole pipeline. It starts executing the whole pipeline. So you have this distinction between these 2 parts. You don't have this distinction in coroutines. So let's try to compare both solutions in several situations which occur frequently when you write asynchronous applications. So first, a very simple thing, sequential code. So let's suppose you have an asynchronous function which gets some data about a user, and you have a regular function which gets some data about an account. And now you want to compose them. So you want to write an asynchronous function which first gets some user data, and then some data about an account, like an account number, for example. So with Kotlin, that's quite straightforward. There is nothing really fancy about that. You treat the output of one function as an input of the other one. For reactive libraries, for composition, you have to use a map operator. So here we have an asynchronous function getUser, which returns a mono. So a mono is a reactive type which it's like a stream of 0 or 1 value or an exception. So basically, it's an equivalent of the suspending function which you see above, but written with the reactive library. So when you want to write the same kind of function which extracts account number, you have to compose those functions using map. So up until now, it's all fine, except that the code with Reactor is a bit not as clear as the one above. But let's suppose that our getAccount function, it now is no longer a regular function, but it's also a suspending function. When we change it to a suspending function, then for Kotlin, nothing really changes. Our getAccount number function is the same. We don't have to change the code at all. But for reactive libraries, if we use reactive libraries, a couple of things change. So our getAccount function now no longer returns account, but it returns a mana of an account. So our code no longer compiles. So instead of extracting an account number from the getAccount response, we have to use a map function. We have to extract that value which is inside that mana. But now the first map is a problem, because if we compile the code like this, what you would get as a response from getAccount number is a mana of a string. So what we have to do is we have to do a flat map. Now this may be a problem in the long term. If you don't know beforehand if your function is a suspending function or a regular function, then with coroutines, in many cases you can get away with it because the compiler will take care of it. As we've seen, we didn't have to change the code of our getAccount number function. But with reactive libraries, that's a problem, because not only we have to change the signature of our function, which now is an asynchronous function, but we also have to change these places in our code where this function is used and for example, to change all maps to flat maps. So that's kind of a problem if you have like a large application. So if you have an asynchronous application, it means that our code executes in different threads. We no longer have this nice single-threaded model. So some part of our code will be executed using one thread, the other one using some other thread. So the question is, how can you somehow control what kind of threads are used for our asynchronous code? So the answer, of course, is yes. So with coroutines, like every coroutine has something which is named coroutine context. It defines many things. Among them is a coroutine dispatcher. So a coroutine context can be a coroutine dispatcher, which is responsible for dispatching the coroutines on some threads. So it actually decides what threads are used to execute a coroutine. And we can create our own coroutine dispatchers. There's a number of ways you can do it. So one of them is to use some built-in functions like new fixed thread full context that you see here. Here we create this coroutine dispatcher, which has a thread pool of 5 threads, and they are named like user 1, 2, 3, etc. And to use a coroutine dispatcher, we have to use a function called withContext. WithContext takes one single parameter as one single parameter of type coroutine context. So this way we specify that everything between the curly braces after withContext is actually executed using this coroutine dispatcher, so it will use those threads. But sometimes you want to have an architecture where a piece of code is executed using one thread pool and the other one using some other thread pool. Like, for example, let's suppose that now we also have a function which calculates an encryption key based on the username. And it takes quite a lot of time to do it. It's a CPU-intensive operation. So we want to limit the number of those operations so that not all of the cores of our CPU are actually taken by this function. So what we can do is we can define a second coroutine context, especially for this encryption operation. And now we have a situation where the get user encryption key will use the threads for the encryption thread pool just for the encryption, and the get user, we actually use the coroutine context with the second thread pool, because you can nest those coding contexts. Now we can achieve actually the same thing with Reactor, but here we do it a bit differently. So to specify that you want an initial operation, an initial stream, or the initial code which produces the values to be used, so that it uses our own thread pool, we have to use scheduler. So the equivalent of a coroutine dispatcher in the reactive world is a scheduler. And we can create our own schedulers, of course, like here. And if we specify, if we use the operator subscribe on, when we specify some scheduler, then the whole pipeline will start executing on this scheduler, so on one of these threads that are part of this scheduler. Now, if we want an operation to be in our pipeline to use a different scheduler, then we have to use a publish on operator. So in our flow, we can define only one subscribe on, because the other ones will be ignored. And this is like the source scheduler. And then every time we use publish on, then the operations after publish on will use the other scheduler. So the model is a bit different. We still can select which threads are going to be used, but we do it in a bit different way. So if we have multiple threads, there is one problem. When we have a single-threaded model, there is this nice thing in the JDK called Threadlocal. So Threadlocal means that we can attach a variable to a thread and set its value in one part of the code and retrieve it in some other part of the code. It's used for many things. So for example, if you have an incoming request and you assign an ID of this request, you can set this ID as a thread local so that you can retrieve it later on in some other parts of the code to, for example, correlate some things to put it in your log output, etc. It's also used for things like security or transaction management. So it would be nice to have this kind of behavior with either coroutines or reactive libraries. So with coroutines, so there is this coroutine context that I mentioned, and it also can be used for things like these, like thread local. But the way to do it with coroutines is what we would like to have is to be able to extract the value from the thread local. But if we change the thread, that thread local variable is no longer there. So what we can do is we can actually use a context which preserves value of a thread local. So there is this nice extension function on a thread local called asContextElement, which produces a coroutine context. And this coroutine context has this special behavior that when you change a thread, then before the coroutine starts running in that thread, the thread local variable is restored. So in our case, what happens is if you call getUsername, then the request ID, the thread local variable will be read, the value of that variable will be read and put in a context. And then that context will actually be propagated to all the code, all the calls, all the coroutines that will be used inside this context. So the login getUser will actually be able to read that value from a thread local. Now, you can actually think of it as a read-only thread local variable because you can't set the value. You can only read the value because if you set it, then it will not, that change will not be reflected, will not be propagated to the coroutine context. So it's a read-only thread local, but it's enough for almost all cases of using thread locals. Now, the same thing can be actually achieved with Reactor, and this is actually one of the reasons I chose Reactor, because for me, it's the only known to me, at least, reactive library which has this functionality of propagating a context. So we can't really achieve what I've shown you here. We can't read a thread local in our reactive pipeline. With Reactor, we do it in a bit different way. We use something which is called subscriber context. So in our operations, in our reactive pipeline, we can get the value of the subscriber context by calling the subscriber context static method. This method will return either a mono or a flux, depending on what reactive types you use. And from there you can extract some values, some context. So the question is, how do we specify what should be inside this context? And for that, we can use a subscriber context operator. There's a special operator on the reactive pipeline where you specify the initial context which will be propagated. So what happens here is when you call getUsername, then this subscriber context is created. And the context itself is like a map, like a key value pairs. And here you will have a key request ID and the value, which is read from the Threadlocal, and this context will be propagated through the whole pipeline of operations so that you can access it with this subscriber context static method. So far we've seen only a happy path scenario, like nothing failed. But in the real world, things fail. So we have to have some form of exception handling. So how do we do it? With coroutines, that's quite straightforward. We use regular language constructs. And this is actually something which I want you to pay attention to, because so far we've been using mostly regular language constructs of Kotlin with like one or two supporting functions, whereas with reactive libraries, we had to choose some operators, some concepts from reactive libraries. This is one of the strengths of coroutines, that you don't have to learn the names or semantics of new operators like you have to do it with reactive libraries. But getting back to our exception handling. So with exception handling, we use try-catch, like in our regular code. There's nothing really unusual here. With Reactor, we have to use, of course, one of the operators. There's like a couple of them defined in Project Reactor. You can, for example, use onErrorReturn. In our onErrorReturn, we specify the value that will be delivered if there's an exception thrown in our pipeline. We can also use things like onErrorResume, where we specify a mono from which a value will be extracted when there's an exception thrown. So there's like some dynamic behavior introduced here. Or you can use an onErrorMap, which will just map the exception that was thrown. So as you see, the code here, it's with coroutines, it's quite straightforward. With Reactor, we have to turn into functional style. So if we have exceptions, then we sometimes want to retry operations. Because let's say that we have an asynchronous function which accesses some database server over a network, and the network is unreliable. It may lost packets or something like this. So sometimes we just want to retry after some delay the same operation because the network may just start working. So how do we retry with these both solutions? So with Kotlin, again, we don't use anything fancy here. We use regular language. There's a loop here, which tries to execute an operation up to 5 times. And if it fails, then the last exception that was thrown by the getUser function will be just thrown from our retrying getUser function. And there's a delay between those calls. So if there is an exception, then we wait for half a second, then we wait for a second, then for a second and a half, etc. So there is some policy implemented here. In fact, what you usually do is you have this policy as some supporting function because you want to reuse that policy in many places in your code. So what you usually do is you extract that logic into some higher order function where you specify like how many times you want to retry, what's the initial time between retrials, and the function that you want to call itself. And then your code is a bit, or not even a bit, it's more readable. So the question is, can we do it with Reactor? And the answer is yes. I mean, the reactive library designers thought about it too. So the way to do it with Reactor is you have to use a special operator called retry when. And it has a very, well, let's say for me it was non-intuitive semantics. So retry when takes as a parameter a function, and this function itself takes as a parameter a flux of throwables, and as an output, it produces a flux of long values. So the flux, the input flux of throwables are these exceptions thrown from the upstream. So if the upstream operations fail, they throw an exception, and this is delivered via this input flow. And then we have this output flux. The output flux, it actually determines if we are going to try, because we can just close the output flux, which means we don't retry anymore, or we just deliver some value. But the important thing is not the value itself, but the time that we wait before we deliver the value, because the flux is like a stream of values, possibly infinite stream of values, but it's sort of like a sequence, but it's a timing factor. These values are delivered at certain points in time. So the way we do it is we take an input flux, there is an exception, and we say, okay, so let's wait half a second. So in the output flux, we will deliver some value, but after half a second. And this way, our reactive pipeline will know that, okay, I have to retry the upstream again. So that's a bit convoluted. I actually implemented the same kind of policy that you've seen before with coroutines. I've implemented the same kind of policy with Reactor, and I will not go over this function, but it's a bit more complicated than the one with coroutines. So far we've seen only sequential code, but since we have asynchronous calls, we can try doing some concurrent code where when we invoke a few operations concurrently at the same time. So let's suppose that we have two asynchronous functions. One will get some data about the user, and the other one gets some data about the user's roles. And we want to define our own function which returns both of them. So to do it, we have to use a function called async. Async is actually an extension function on the coroutine scope. I will get to what coroutine scope is in a moment. But the way async works is you provide to async a function or lambda that will start being executed in some background thread in some coroutine dispatcher. And the result of async is a deferred. So deferred, if you've ever worked with any kind of promise type libraries like or types like computable future or even reactive types are actually kind of promise type objects, then this is very similar. Deferred is something which will deliver you the value because it has an await function. So async will return a deferred, and when you call await on this deferred, then your code will be suspended until there is a value delivered or there's an exception thrown. But the important thing is that the await function is a suspending function, so you will not block the thread when you call await. So here we launch two coroutines. In one coroutine we use getUser, in the other one we use getRoles, and then we await for both of the results and combine them to a pair of values. So that's quite straightforward. They are running concurrently, so it will take only the time, the longer time of execution of either of those functions. And there is this coroutine scope. So coroutine scope, it gives you a few things. One of them is that if you launch a new coroutine in your coroutine scope, then before this coroutine scope is sort of like closed, or before you finish, essentially before you go out of, before the last curly brace, all coroutines should finish its execution. There is no way that you will be left with some hanging coroutine running in some background thread if you are in a coroutine scope. So, in our case, it means that if any of the await functions throws an exception, then the other coroutine will be cancelled. Because coroutine scope also manages these coroutines. We launch two coroutines, one runs getUser, the other one runs getRoles. So let's imagine a situation where we have a getUser function which takes a very long time to execute. And we have a getRoles function which fails almost immediately. So if we didn't have this coroutine scope, when we call await on user, on this deferred of user, we would wait a very long time. We would get the value of this user, and then we would call await on the roles, on this deferred of roles. And then we would get an exception. So it's not really good to have this kind of behavior, to wait a long time only to learn that we didn't have to, in fact. So what coroutine scope does is, if any of the coroutines, which is inside this coroutine scope, if any of the coroutines fail, then all the other coroutines are cancelled. So in our case, if the getRoles throws an exception, then the coroutine scope knows that it should cancel all coroutines. So it cancels the coroutine that runs getUser. So your user await will also throw an exception. So we will not wait this very long time for the getUser to finish. That's a very nice behavior. And in fact, the same kind of behavior we have with reactive programming. With reactive programming, if you want to run two things concurrently, we can use, for example, a zip operator. So here I use zip with, which zips two monos. And the function that we provide to the zip with operator will be executed once both of the values to both of these monos will be delivered. And also reactive or reactor provides this kind of functionality of cancelling the mono if the other ones throws an exception. So here the solution with reactive programming it's nicer. It's nicer because coroutines were designed for sequential code. It's not like the sequential asynchronous code was this thing that coroutines shine, is this thing that coroutines shine. And the concurrent code is not as nice, and this is actually by design. So the designers of Kotlin coroutines, they said that concurrency is a very hard problem, and they want to have it put explicitly in the code so that you see that something unusual happens here. But I started to think about different situations where maybe reactive programming, the code with reactive programming might be not as nice as this one. So I came up with a situation where we want to cancel a coroutine ourselves. So let's suppose that we have the same situations as before. But now a user may be blocked. If a user is blocked, then we want to return empty roles, and we actually don't care about what roles a user really has. So what we do now is we wait for a user. If that user is blocked, we cancel explicitly by calling cancel on the deferred. We cancel the coroutine and return empty as roles. Otherwise, we just wait for the roles. Now, I tried to implement the same thing with Reactor. So I asked a couple of smart people about how to do it. They came with different versions, and I combined them and added something for me, and this is what I came with. It's not nice. If you know any better solution, then just let me know. But this actually shows that while in these simple scenarios, the reactive libraries the solutions with reactive libraries are actually quite nice and quite succinct. If you have something more, like slightly more complex situation there, then maybe coroutines are better. So let's try something with parallel code. So by parallel code, I mean that we have a function which we want to invoke for like a single function, but we want to evoke it for different parameter values. So for example, we have an account. An account has a couple of users, and we want to get a list of users. And and you have only two functions, one which returns user IDs, and the other function which just returns a user, and both of them are asynchronous functions. So we just want to make a bit more complex composition. So what we can do is we can create a coroutine scope, where in this coroutine scope we will launch a coroutine for every call to get user, and then we will gather all the responses from all the coroutines. So we call get user IDs, that will give us a list of users. Then for every list of user IDs, then for every user ID we'll launch a coroutine which will call get user, and then we will just await for all coroutines to finish the execution. And by using coroutine scope, we make sure that if any of the get user fails, then the whole thing will fail. So again, the code is quite straightforward. With reactive libraries, with Reactor, the code looks like this. And it looks like this because we use here a mono of a list as a model of our list of user IDs or list of users. So we have to first convert a mono of a list to a flux, and then convert it back from mono of a list of users to from flux of users to a mono of a list of users. So that's a very convoluted way of writing it. This is not the way that we would have done it if we wanted to do it properly. We probably would have used flux directly. And now the code looks much simpler with Reactor. So this is probably the one that is better in this situation. So I said something about flux. This is like this possibly infinite stream of values with this timing factor. And in fact, with coroutines, we have a similar concept. And this is channel. So channels, they are still, I think, experimental API in Kotlin coroutines. But they are close to being a stable thing, so I think the API will not change that much. Now, channels and coroutines, they allow you to, you can send a value to a channel and you can receive a value from a channel. So it's sort of like a queue. Only that, like you have in Java, you have queues, which have these operations for putting some value in a queue and getting a value from a queue. But these functions or these methods are either blocking methods, so that, for example, you want to read something from a queue, but there's nothing in that queue, then you either block, your thread is blocked until there is some value in that queue, or this function will return a null value or throws an exception or something. And then you have to do some spin looping to actually achieve something. So channels in coroutines are a bit different. So they also have the, well, first of all, we have receive channels and send channels. And the channel itself is both a receiving channel and a sending channel. So when the operations to send and receive values to and from a channel, they are suspending functions. So what does it mean? If we want to send something to this channel, so we call send, and there is no one on the receiving side, then our send function will be suspended until someone receives something from that channel. And the same goes for receiving side. If you want to receive something from a channel, and there is nothing in that channel, no one is sending anything, then it will be suspended until someone actually sends something to that channel. So this is a very nice behavior. It's very similar to a backpropagation, backpressure, which we'll get in a moment. But this is this is the difference between the channels and the queues in the JDK. So how do we use channels? So we have this receive function which receives some value. For example, here we just get a list of users and as a receive channel, and then we print the names of these users. We also have a function called receive or null, which will, because receive will actually if a channel is closed, then the receiver will throw an exception. So this is not a nice behavior. If you want to do it more elegantly, then we may use receive or null, where it will return a null value if the channel is closed, or we can use a very useful function called consume each, where you just provide a function which will be called for every message in that channel. With reactive libraries, it's very similar to the consume each approach, where you call subscribe and you provide your own sort of like a callback, which will be called for every value in that stream. So the question is, how do we generate these streams? Like, how do we make flux, or how do we create channels? So to create a channel, we call the channel function, and then we launch a coroutine. This is what we usually do. We launch a coroutine, and this coroutine actually does all the sending and closing things. Like here, we create a channel of a user, and since channel is both a receive channel and a send channel, then we can actually make this function return a receive channel. We launch a coroutine with launch. It just launches this coroutine in some background thread, and then it sends some values. And this is actually, okay, so let me first, okay, let's see the simpler form. There is a produce function. The produce function is equivalent to what we've seen just before. It creates a channel, and it lets you use that channel inside that lambda that is a parameter of produce. That's a very common pattern. This is why this produce function exists. For reactive libraries, we have like a number of things we have to, we may actually do to create fluxes. Here I present just the simplest one. We call the generate function. The generate function takes as a parameter a function itself, which has one parameter sync, and the sync, on the sync we can call next or complete to deliver values or close the flux. Now there is one important thing, but one important difference between these two solutions. So channels are hot streams. Now there is the difference between a hot stream and a cold stream. So a hot stream is something that produces values, and you just plug into it, and you just receive values from the moment you plug into it. The cold stream will not deliver values until you subscribe to it. This distinction is in the reactive libraries. In coroutines right now, we only have hot streams. So channels are hot streams. There is some preliminary work done for cold stream as well. Actually, about 2 weeks ago, some initial design documents, some initial implementation came out. But I will not show you that because that may change in something completely different. But for now, you can use channels which are hot streams. So it means that if you call produce, like if we have this example here, if you call produce, then the code inside this produce will start being executed immediately, and it will start sending the values. If we call generate with reactive libraries, the function inside generate will not start being executed until you subscribe to that flux. So this is the major difference between these two things. Here we have a cold stream on the with the reactive library. With the coroutines we have hot streams. So both reactive libraries and channels have operators. Like for reactive libraries, we have multiple operators, like I don't know, hundreds probably or something. For channels, we also have operators which are similar to the ones with reactive libraries, only that since the channels are hot streams, then here, if you call filter not or map, then actually what will happen is for every operator, a coroutine will launch, which will read the values from the upstream channel and send the value, or not send the value if it's filtered out. But essentially, it will produce values to some output channel. So here we set up, if we create a code like this, it will launch several coroutines, like for every operator, at least one coroutine. For reactive libraries, it doesn't work this way. We just set up the pipeline of operations, and they will be executed only when we subscribe to it. But there is one good thing, which is because here we actually may have hot streams and cold stream with reactive types with coroutines not. But if you want to define a custom operator for reactive libraries, that's a very difficult thing to do. Like, for example, I've had a look at the map and filter operators, and it's like several hundred lines of code. Whereas with coroutines, that's quite simple. With channels, it's quite simple to create your own custom operator. So here we have an example of an operator called filter map, which does filtering and mapping in one go, so that you define your own function. If it returns a null value, then it just filters out. If not, then it's just mapped. And you can see here that it's quite simple, quite straightforward to do. So with channels, it's really very easy to create your own operators. Now, I mentioned back pressure before. So when we create a channel, and we, like I said, if we try to send a value to a channel and there's no receiving side, then we are suspended. But that's not something that we always want to, that's not the behavior we always want to have. Sometimes we may want to have like sort of like a buffer maybe between the sender and the receiver. And you can actually achieve that with channels. Now, I will try to pronounce a French word, so I'm sorry for my French, I haven't learned. Like I've practiced this word for the past few hours. But so, and like the default channel in coroutines is rendezvous channel, okay? So it means that it has this behavior, like you send a value, if there's no receiving side, then you just wait. But you can create a buffered channel, so you can specify a parameter to this channel function, which creates a channel, and if this parameter is an integer, it's like an int value, it's actually a size of a buffer between the sender and the receiver. So that, let's say you call a channel with 5, which it means you can call send 5 times before it gets suspended if there is no receiving side. There's also a special kind of channel which is called conflated. Conflated means that the receiver will always see only the latest value that's in this channel when it tries to receive the value. So if you produce like multiple values, one after the other, and the receiving side just gets one value and does something with that value, but these values are produced by the sender, then the values themselves are lost. I mean, all except the last one that will get delivered to the receiver. So this is useful if you have things like, for example, you measure a temperature of something, and you send just the values of this temperature, so you usually are only interested in the last value. You may actually skip a few values, it doesn't really matter. And you have the same sort of behavior with reactive libraries. There are some different back pressure strategies. Now, we've seen that there are some advantages and there's disadvantages of both of these solutions. So the question is, can we somehow mix them? So the answer is yes. So there are some interoperability libraries which allow you to mix both of these solutions, so that you, for example, can, if you have a function which returns a reactive type, a mono, then you can easily create a suspending function by using one of the extension functions like await first or null or await first. There's a number of those functions. We just take a reactive type and convert it into a suspending function. And the same thing applies if you want to do it the other way around. So if you want to create a mono of something and you have a coroutine, then it's quite easy to do with the mono function. The same thing applies to flux. It's not only mono, it's also about flux. So the other side of fluxes are channels. So we can convert a flux to a channel and the other way around. So the takeaways from this presentation. So if you have a sequential code, then coroutines are almost 100% better than reactive libraries. If you have concurrent code, that depends on whether your code is complex or not. And you have to be aware that channels are now experimental. They are always hot streams, but the API will probably not change that much. And as always, you can mix both of these solutions, so you can pick the one that you want for the case you have. If you want to know more, there are two guides that are very nicely written that cover these topics. So the first one is actually targeted at the reactive streams. This is Guide to Reactive Streams with Coroutines. And the other ones is just like a general coroutines guide, but it actually contains also a lot of information which may be useful. That's all from me for today. I'm 1 minute past time. I don't know if you have time for questions, maybe, like a few minutes or something, or? No? Okay, so if you have any questions.
One question, or just ask a question when you will be outside, as you prefer. Maybe one question?
Maybe one. Anyone has a question? Looks like the problem is solved. Yeah. Okay, thank you.